Today we are going to be talking about sectors and linear speed and angular speed. So first of all, let's talk about what a sector is. A sector is just a portion of a circle that includes two sides, which are the radii of the circle, and an included or what's called a central angle and an arc. So it has the two radii, a central angle, and an arc. Okay, the arc is the outside of it. So it's a part of a circle. It's a little section or sector of a circle. Okay, we would like to be able to find a formula that we can use for the length of the arc of the sector. Okay, called the arc length. Okay, the entire circle would be composed of 360 degrees or 2 pi radians, and the entire circle would have a length, a circumference of 2 pi r. So I want to know what L is. I'm looking for L, and it has a central angle of theta. But I know that the entire circumference is 2 pi r, and the entire quote central angle then would be 360 degrees if we're in degrees. Okay, it would be 2 pi if we were in radians. I'm going to come next door here and we're going to do the same thing in radians. So L over theta is 2 pi r, that's the circumference, divided by 2 pi radians, because 360 is 2 pi radians. Over here, if I solve this for L, I would have L is equal to 2 pi r times theta, I'm multiplying both sides by theta, divided by 360 degrees. That's our formula for the arc length if theta is in degrees. But if theta is in radians, L will be, look what happens over here. The 2 pi's cancel, and when we multiply by theta, we just get our theta. If theta is in radians, this is our formula. If theta is in degrees, this is our formula, which we can reduce and make it pi r theta over 180 degrees. Okay, but still, which one is easier? This one is easier. So this is going to be the one that we use. We're going to be using theta in radians because it creates a much simpler formula for us. So for a sector of radius r and central angle measured in radians, it has to be measured in radians, the arc length, L, is given by L is equal to r times theta. A really easy formula for us. So let's determine the length of the arc of a sector with radius 10 centimeters and central angle pi over 3. The length would be the radius times the angle. As long as we're in radians, it has to be in radians. So this would be 10 centimeters times pi over 3, which is 10 pi over 3. And the units for that would be the same as the units for the radius. This would be in centimeters. 10 pi over 3 centimeters. Let's determine the length of the arc of a sector with radius 3 feet and central angle 240 degrees. Okay. Think about that. This first one, I drew that. The first one would have an angle of pi over 3. So pi over 3 is 60 degrees. So we're looking at this part. We found L when each of our radii were 10 centimeters. And this is pi over 3. Okay. Now we want 240 degrees. 240 degrees is down here in the third quadrant. 240 degrees. And we're looking for L if the radii are 3 feet. Okay, so we're finding that length. Alright, so L is equal to R times theta, but only if theta is in radians. And R theta is not in radians. So we're going to convert it to radians. 240 degrees times pi over 180 degrees, that's our conversion, right? The degrees cancel, a 0 cancels, 24 over 18, there's a 6 in each of those. There's 6 in each of those, so that would be 4 pi over 3. 4 pi over 3. 4 pi over 3. Now we have theta in radians, and now we can use our formula. 3 feet times 4 pi over 3 radians is 4 pi. And our units would be in feet. Okay, so that is how we find the length of an arc of a sector. Now we are going to be finding the area of a sector. Okay, to determine the formula, we're going to use the same process that we did for the length of a sector, of the arc length of a sector. So the area of a sector, well, the entire circle has an area of pi r squared. So if we know we want to know the area. I'm looking for area. I'm going to call it A for area. The area for some given theta, central angle of theta, will equal the entire circle area, pi r squared, divided by either 360 degrees or 2 pi, depending on if this theta is in degrees or radians. I'm going to again come over here, set up the same formula, but put 2 pi over here. So this would be if theta was in radians. On this side, if I solve for A, I'm multiplying both sides by theta, and I get pi r squared theta divided by 360 degrees. That's our formula if theta is in degrees. But if theta is in radians, when I multiply this over, the pi's cancel out, and I'm multiplying by theta, and I'm going to write, instead of dividing by 2, I'm going to write that as 1/2 r squared theta. Again, a simpler formula. It's valid only when theta is in radians. So for the area of a sector with central angle theta measured in radians, the area A is given by A is equal to 1/2 r squared theta. Again, it has to be in radians for this formula. Anything that I have boxed with a star means you must memorize it for the test and for any test, quiz, whatever. Okay, let's determine the area of a sector with central angle 2 pi over 3. That's in radians, so check on radians, and the radius of 4 inches. And this time we're going to indicate units of measure. So the area will be 1/2 r squared theta. R is 4. Theta is in radians. 2 pi over 3. This would be 1 times 16 times 2 times pi. So 32 pi. I don't know why I did that. I'm going to cancel out these 2's. Okay, and then I have 16 pi over 3. What would be the units? Well, I multiplied 4 inches times 4 inches. So I'm going to be in inches squared, square inches. 16 pi over 3 square inches. Let's now determine the radius. Up here we were determining the area. Now we're going to determine the radius of a sector with central angle 3 pi over 4 and area 24 square centimeters. Well, they gave me the area, so I'm setting up the area formula. This is the area formula. A is equal to 1/2 r squared theta. We must know that. They gave me that the area was 24. I don't know r, but I do know theta, 3 pi over 4. Okay, I'm going to take this 24 over here. I'm multiplying the 24 by 2 and 4, so I'm multiplying that by 2 times 4. I'm dividing that. I should have gone to the other side. Let me go over here. I'm running out of room. I'm taking the 24, I'm multiplying by the 2 and the 4 because those are in the denominator. I'm dividing by 1 times 3 times pi, so I'm dividing by 3 times pi. And that will give me r squared. 3 goes into 24 8 times. 8 times 8 is 64, so I have 64 over pi is equal to r squared. Square root both sides. We're not going to be able to have a negative radius, so you ignore the negative that you get when you square root. R will be 8 over the square root of pi. 8 over the square root of pi. Now, we're going to get used to doing this, so you might as well start now. We do not want to have a square root in the denominator. On the AP exam for pre-calculus, you cannot have a square root in the denominator. Once you get to calculus, it's fine. But for pre-calculus, they don't want that. So I'm going to multiply top and bottom by the square root of pi. This is called rationalizing the denominator. And we get 8 square root of pi on top, and on the bottom we get pi. The units for this, even though they didn't ask for that, would be in centimeters, because the area was square centimeters, the radius is in centimeters. Now let's determine the central angle. Let's determine the central angle of a sector with radius 3 inches and area 30 square inches. Still using area as 1/2 r squared theta. We know that the area is 30. We know that the radius is 3. The square of 3 is 9. I'm going to take that 30. I'm multiplying by the 2. I'm dividing by the 9. And that will be theta. So theta is 60 over 9. 60 over, oh, I forgot my one. 60 over 9. Yes? Yes. Oh, that reduces. I'm like, what happened here? 60 and 9 both have a 3 in them, so that would be 20 over 3. Okay? Notice that there's no pi. Radians do not have to have a pi with them. I know my answer is in radians because I used this formula. So if they asked me for units, I would say radians. Radians do not have to have a pi with them. All right? They can just be a number. Pi is just a number. Okay, so keep that in mind. All right. On to something a little different. Linear speed and angular speed. Consider a particle moving along the arc of a circle with radius r. Okay? Consider a particle moving along that arc. Linear speed measures how fast the particle is moving. On its arc, how fast the particle is moving. That's its speed or its velocity. It's how fast the particle is moving. Examples of units for linear speed would be like miles per hour or feet per second or meters per minute. Okay, all of those. Angular speed measures how fast the angle is changing. How fast the angle is changing. Okay. So, what would be units of angular speed? How fast the angle is changing? That would be in like radians per minute, or radians per second, or radians per hour, or radians per any unit of time, or degrees per minute, or hour, or second, or day, or year, whatever. Any unit of time. It is conventional to call linear velocity a lowercase v, and to call angular velocity the lowercase Greek letter omega. It looks like a very curvy W. When I draw it, I do that. It's a very curvy W. Okay? That is angular speed, or angular velocity. For a particle moving at a constant speed along a circular arc of radius r, if L is the arc length traveled in time t, then the linear speed would be L over the time. It's how many meters it went in that amount of time. So V is just L over t. Miles per hour, meters per second, whatever. That's the length of the arc divided by the time. For the angle, very similar. The angular speed, omega, is equal to the central angle divided by t, whatever the central angle is, divided by t. Okay? Radians per second, degrees per year, whatever. Okay? All right. Now, keep in mind that theta, for our L, theta has to be in radians. So that's why it says in radian measurement. We're always going to stick with radian measurement for here, for these. Okay? Now, since L is equal to R times theta, if I take this and I divide both sides by t, I get a relationship between the linear speed and angular speed. L over t is our linear speed, v. Theta over t is our angular speed, omega. So this is linear speed is equal to r times angular speed. It gives us a relationship between linear speed and angular speed. Okay, so v is equal to r times omega. Linear speed is the radius times the angular speed. Okay, let's take a look at some examples. The second hand of a clock is 10 centimeters long. Okay, 10 centimeters long. Find the linear speed. Find the linear speed of the tip of this second hand as it makes one complete revolution around the clock. One complete revolution around the clock. So V is equal to L over T. That's our formula for linear speed. L is our arc length. L is R times theta. Okay. What is the radius in this situation? The radius is 10 centimeters, right? What is the angle? What is the angle that we went through? It has to be in radians if we're using this formula for L. It has to be in radians. So this is 2 pi. We go 2 pi radians in 1 complete revolution around the clock. How long does it take? How long does it take to go for the second hand to go 1 complete revolution around the clock? We want our answer in centimeters per second. So how many seconds does it take for the second hand to go 1 complete revolution around the clock? It takes 60 seconds. The zeros cancel. 2 goes into 6 3 times. This is pi over 3 centimeters per second. Number 7. The blades of a wind turbine are 116 feet long. Okay, the blades are 116 feet long. The propeller rotates at 15 revolutions per minute. 15 revolutions per minute. Find the angular speed of the propeller in radians per minute. In radians per minute, the angular speed. Well, angular speed is the central angle divided by t, if the central angle is in radians. Okay? So in radians per minute, we know that the propeller rotates at 15 revolutions per minute. Each revolution is 2 pi radians, right? Let me come over here. Our theta, we go 15 revolutions, and that would be 15 times 2 pi radians, which is 30 pi. So theta is 30 pi. Okay? We do that in 1 minute. So our angular velocity will be 30 pi divided by 1 minute, which is 30 pi radians per minute. Okay? They didn't ask for units. They gave me the units, but I'm confirming that. So 30 pi radians per minute. Let's now find the linear speed. How fast are the tips of these blades going? Let's find the linear speed of the tips of the blades. And let's do it in miles per hour. That way we kind of have an idea of just how fast these are going. Okay? So linear speed. What's our formula for linear speed? V is equal to? We can do this 2 ways. The length of the arc over the time, or since we just found the angular speed, this is r times the angular speed, which we just found. Sorry, got something in my throat. So the radius is 116. That's 116 feet. That was in feet, okay? And I'm going to multiply that by 30 pi radians per minute. So 30 pi radians per minute. So if I multiplied 116 times 30, I would get feet per minute. I want miles per hour. Okay? So I know right now I have 116 times 30 pi feet per minute. I want to change that to miles per hour. Let's do the feet first. I know that there are 5,280 feet in 1 mile. So the feet here will cancel, and I'm left now with miles per minute. And now we're going to change minutes to hours. I know that there are 60 minutes in 1 hour. Our minutes cancel. I'm left with miles per hour. That's what I wanted. So all I need to do is multiply the numbers on top and the numbers on bottom, and I have miles per hour. So 116 times 30 times pi times 60 divided by just 5,280, and that will be miles per hour. Want to know how fast these blades go? Let's go to our calculator. Let's type this in just to see. Okay, 116 times 30 times pi times 60 divided by 5280. 124.235 miles per hour. Wow. This was a realistic situation. I looked up the data on how long these blades usually are and how fast they rotate, how fast these blades turn. And this was what it said, about 15 revolutions per minute. That doesn't sound like very much per minute, but that's how fast the tips of these blades go. Interesting. Okay, so that was, today we did length of the arc of a sector, area of a sector, linear velocity, and angular velocity.